Hi everyone, I hope you guys are all safe and doing well during this time. As you know, we are going to continue our lectures in online format. So I'm going to post the lectures, I'm going to just record the lectures in a video format and post it online, probably on YouTube. And you can just ask me questions either through email or just leave a comment under the video on YouTube. And I try to respond to your questions as soon as possible. So, as you know, we had the midterm exam on Monday, and on last Wednesday our class got cancelled because all the class in the university got cancelled. So I thought maybe for this lecture, just to keep everything started in the online format, it's better to just solve the midterm exam. With this, we are going to have the solution for the midterm exam, and also it's a kind of like a good quick review on all the lectures that we had before the midterm exam. So you can see that I have all the four questions that we had for the midterm exam, and I'm going to go through them one by one and solve them. So let's start with question 1. So in question 1, we have the center of mass for the boomerang C. So the center of mass for this boomerang C at point C, which it doesn't overlap with the boomerang structure itself. It's just kind of like the center of mass virtually belongs to the boomerang. So the center of mass of the boomerang C is moving with the velocity of 2 meters per second and acceleration of 10 meters per second square in the directions shown in the figure. So here is the velocity, 2 meters per second. We have the angle with the horizontal direction, and also we have the acceleration, which is a downward acceleration. At the instant shown, the boomerang is rotating with the angular velocity and acceleration given in the figure. So you can see here that we have the boomerang is rotating with this angular velocity in this direction and also the angular acceleration in this direction. So we are asked to find the velocity and acceleration of point A on the boomerang. So here, this is a kind of like a classic examples of rigid body dynamics. We said that for a rigid body, if we have the velocity and acceleration of one point and also the angular velocity and angular acceleration of the rigid body, we should be able to find the velocity and acceleration of any other point of the rigid body. So here you can see that we have the velocity and acceleration of point C, which virtually belongs to the rigid body. We have omega, we have alpha, so we are asked to find the velocity and acceleration of point A. So let's start with velocity. So for velocity, I can write down VA is equal to VC plus omega cross RA with respect to C. So this is the formula that we derived. We derived this formula for the rigid body dynamics. So all I need to do here is just to kind of like substitute these quantities. So we have VA is equal to VC. So VC is 2 meters per second in this direction, which just makes a 30-degree angle with the horizontal direction. So I can say 2. So I should have put a coordinate system here. So let's say this is X, this is Y. So, or I can just put it here, doesn't matter, just the important thing is that the horizontal direction is the X direction. Let me change the color here, maybe with green. So the horizontal direction is just the X direction, and the vertical direction is the Y direction. That's not very good. So this is the Y direction. So we have the VC 2 meters per second in this direction, so that is going to be 2 times cosine 30 in the I direction, the projection of this vector in the X direction, plus 2 times sine 30 in the Y direction. So sine 30 in the J direction, plus omega cross r a with respect to c. So omega here, so if this is x, this is y, this is going to be our z direction, out of plane. So omega is just in the minus, because it is clockwise, in the clockwise direction. We can use also right hand rule. It is in the minus z direction. So I can write down omega as minus 3 k. So the value of omega is 3, the direction is just in the minus k, so minus 3k cross RA with respect to C. So here again we can just use this 0.2 dimension and also this angle to write down the position vector of point A with respect to point C. So we have 0.2 minus 0.2 cosine 60 in the I direction plus 0.2 sine 60 in the j direction. The projection of this position vector in the x direction, which is going to be in the minus x direction, that's why we have the minus sign, and also the projection of this vector in the y direction. So we are going to have VA is equal to 2 times cosine 30. Cosine 30 is just a square root of 3 over 2, so that's a square root of 3 in the I direction, plus 2 times sine 30. Sine 30 is half, so that's going to be 1, so plus j, plus. So here we have k cross I. K cross I is j, and we have minus times minus, that's positive, so we have 0.6 times cosine 60. Cosine 60 is half, so we are going to have 0.3 in the j direction. And here we have k cross j. K cross j is minus I. We have a minus here, that's positive, so that's 0.6 times sine 60. Sine 60 is square root of 3 over 2, so that is 0.3 square root of 3 in the I direction. So it's equal to, so for the I direction we have 1.3 square root of 3 in the I direction, and in the j direction we have 1.3, so 1.3 in the j direction. I think I did the multiplication right, so 3 times 0.6 times square root of 3 over 2, that's 0.3 square root of 3. So this is VA, so VA is equal to this quantity. Now let's calculate the acceleration of point A. So for acceleration, I can write down AA, acceleration of point A, is equal to AC, the acceleration of point C, plus alpha cross R A with respect to C, plus omega cross R. R A with respect to C, so it's equal to, so AC, we have AC, so AC is minus 10J, so minus 10J plus alpha. So alpha is 1 radian per second squared in the positive direction, in the positive k direction, so we have 1k. So I just write down k cross RA with respect to C, and we had RA with respect to C. This is RA with respect to C, minus 0.2 cosine 60I plus 0.2 sine 60J plus omega cross R. So omega was minus 3k, so actually minus 3k cross minus 3k cross R, and here is the R, so I can also just simplify this right down, minus 0.1 in the I direction and plus 1.1 square root of 3 in the j direction. So here is the acceleration of point A. So we just need to simplify this. So this is minus 10j plus k cross I is j, and we have a minus here, so that is going to be a minus sign. So let me make my eraser a little smaller here. Okay. So minus, and here is just 0.1, so 0.1 in the j direction. K cross j is minus I, and it's just going to be minus, so minus, again 0.1, square root of 3 in the I direction, plus here minus 3k times this quantity. So let's just start with here. K cross I is j, and here we have, so j. K cross j is minus I, so we are going to have a minus, and we have 3 minuses here, so that's going to be 4 minuses. That's going to be positive. So positive plus, and it's going to be in the I direction. 3 times 3 is 9, times 0.1, that's 0.9. 0.9 in the I direction. Here, k cross j is minus I. K cross minus I is minus j. So we have a minus, and again we have a minus here, that's positive, so plus 0.9 the square root of 3 in the j direction. 0.9 the square root of 3, k, well actually I think it's going to be minus, so k cross j, that's a minus I, that's 1 minus, 2 minus, and 3 minus, so that's going to be a minus sign. So here. So that's it. We did all the multiplication. So the acceleration is going to be in the I direction. We have minus 0.1 square root of 3, and here plus 0.9. The I direction plus the j direction, we have minus 10, minus 0.1, so that's minus 10.1. And here we have minus 0.9 square root of 3 the j direction. So we had all the terms here, I terms here, and also the j terms. So that's for the acceleration of point A, that we were able to just write it down based on point C. So let's go to the second question. For the second question, we have a slider C is moving inside the groove with a velocity of 2 meters per second in the direction shown in the figure. Find the angular velocities of link AB and BC at the instant shown in the figure. So we have this slider moving inside this groove in this direction. We have the angle of the groove with the horizontal direction. We have the velocity of this slider. We have the length of these two links AB and BC. We are asked to find the velocity of the angular velocity of AB and angular acceleration of BC. So the way that we can solve this problem is that I can write down the velocity of point B based on point A, because so these 2 points, both of them belong to this rigid body, to the AB, and by writing that the velocity of point A is 0, so we have the angular velocity of link AB as an unknown. So if I write down the velocity of point B based on A, we are going to have one unknown, two unknowns actually. We don't have the velocity of point B. So VB and angular velocity is going to be, angular velocity of AB are going to be unknown. For for the second stage, I can write down the velocity of point B based on point C, because both of them belongs to this rigid body. And here we have the velocity of point C. So if I do that, we get another equation that has two unknowns again, VB and also omega BC. So at the end, we get two equations that has two unknowns, VB, which is unknown in both of them, and also omega AB and omega BC. So that's actually three unknowns, but we get two vectors, two equations for vectors to be equal to each other. VB, the velocity of point B, is going to be a vector when we write it based on A, should be equal to VB when we write it based on point C. So we can get actually four equations that way, because the I terms should be equal and also the J terms should be equal. So we should be able to find omega BC and omega AB. And actually here we don't need to find VB, but once we find this angular velocity, we can also write down the velocity of point B. So let's start writing the solution. VB is equal to VA plus omega AB cross RB with respect to A. So this is equal to, VA is equal to 0 because that's a pinpoint. So this is 0 plus omega AB. We don't have omega AB, so I just consider unknown quantity. So omega AB in the K direction. So again, this is, let's say this is the I direction, X. This is the Y direction. So omega AB is going to be perpendicular to the plane, to the XY plane. And here I just assume that its quantity is just omega AB in the K direction. So omega AB in the K cross RB with respect to A. RB with respect to A is just 1J, so cross J. So we are going to have K cross J is minus I, so that's minus omega AB in the I direction. Now let's write down the velocity of point B based on point C. So we have VB is equal to VC plus omega BC, omega of this link, cross RC with respect to B. So this is going to be VC. We have VC, so that's 2 meters per second in this direction. So that is going to be 2 minus cosine 30 in the I direction, projection of this vector in the horizontal direction, plus sine 30 in the J direction, plus omega BC. Omega BC is unknown, so we just consider omega BC in the K direction cross RC with respect to B. RC with respect to B is just minus 1.5 in the I direction, so minus 1.5 in the I direction. So this is equal to cosine 30 is the square root of 3 over 2 times 2. That's going to be, here we have a minus sign, minus a square root of 3 in the I direction. 2 times sine 30, that's 1, so plus J. And here K cross I is J, so we are going to have minus 1.5 omega BC in the J direction. So we get VB equal to, in the I direction, that's minus the square root of 3 in the I direction, plus 1 minus 1.5 omega BC in the J direction. So we got this value for VB, also we got this value for VB based on link AB, so they should be equal to each other. So here I would say VB based on A should be equal to VB based on C. So VB over there is just minus omega AB in the I direction. It's equal to VB based on C. So that's minus 3 minus square root of 3 in the I direction plus 1 minus 1.5 omega BC in the J direction. So here we get two equations. So the I terms should be equal to each other, and also the J terms should be equal to each other. So here we have minus omega AB is equal to minus square root of 3. And here we don't have any J component, so that's equal to 0. And here we have 1 minus 1.5 omega BC. So here just we have two equations, two unknowns. We can easily find them. So omega AB is equal to a square root of 3. Its dimension is going to be radian per second. And also omega BC is going to be 1 over 1.5. So that's going to be 2/3. Again, radian per second. And now that we have this omega AB and omega BC, we can go back to our equation for VB and just substitute, for example, here omega BC to find the velocity of point B. But here in the question, we are only asked to find the angular velocities of link AB and BC. So that's for question 2. Let's go to question 3. So in question 3, we have, so in the figure below, the ant is moving on the rotating bar AB with the given velocity and acceleration relative to the bar AB. So we have an ant moving on the bar AB. It is moving with the velocity of 0.5 meter per second in this direction, and also the acceleration of 5 meter per second squared in this direction. We have the dimension of AB and also the angle that it makes with the horizontal direction. So the bar is rotating with the clockwise angular velocity of omega 2 radian per second. So that is going to be, let me use another color. So 2 radian per second in the clockwise direction. So the AB is just rotating in this direction. I don't know why I can't write here. Let me change the color again. For some reason my pen is not working. There we go. So let me erase these things. Okay. So omega is going to be in the clockwise direction. So, oops. Omega is in this direction, and its value is just 2 radian per second. And the angular acceleration is in the counterclockwise direction, so that's going to be in this direction. Alpha equal to 1 radian per second square. What is the velocity and acceleration of the ant with respect to the inertial frame xy? So we have the inertial frame here. We have the relative velocity and acceleration of ant with respect to AB. We have the angular velocity and angular acceleration of the link AB. So we should be able to find the velocity and acceleration of this ant moving on this rigid body. So this is basically a particle moving on a rigid body. This ant is not a point of the rigid body anymore. So we have to use our formula that we derived for a particle moving on a rigid body that is rotating. So VA, I can write down VA, V, so A for ant, VA let's just call it this, V ant is equal to VO, VA actually, this is point A. So VA plus omega cross R ant with respect to A, so omega cross R ant with respect to A plus R dot, the velocity, the relative velocity of that particle, this ant with respect to the rigid body. So this is going to be R dot of ant. So basically this is the formula that we derived. We said that we are gonna just attach a rotating frame to this rigid body. So basically this is how we have considered this problem. So we can just attach the rotating frame here. This is x, small x, this is a small y. That this frame, its initial direction is just like this, and it is just rotating with the angular velocity and angular acceleration, that angular velocity and angular acceleration of the bar. You can also consider it like this. Just consider the x along the AB direction. That actually makes it easier. So let's do that. Let's consider AB, the rotating frame this way. So this is going to be x direction. This is going to be in the y direction. And this frame is rotating with the rigid body, with the AB. So here we are going to have, so that's our formula for the velocity of ant. V ant is equal to VA plus omega AB omega AB cross the position vector of ant with respect to point A plus R dot, the relative velocity of ant with respect to bar, which is R dot. So this is equal to, so here we have VA is equal to 0 because A is a pinpoint, so this is 0 plus omega AB is just 2 in the minus k direction here, so we are going to have minus 2k cross R ant with respect to A. So because the way that we have considered our rotating frame, we have this dimension, so this is basically 10 in the I direction. So 10 in the I direction. Plus R dot. R dot here is just half a meter per second, again in the positive I direction. So plus half I. It's equal to, so 0, that's 0. K cross I is J. We have a minus here, so that's going to be minus 20 in the J direction plus half in the I direction. So that's the velocity of ant, V ant. And if you want, you can just, you can bring this velocity, you can write down this velocity vector in the inertial frame here, because we have asked for the velocity and acceleration with respect to the inertial frame. This is fine. This is just a velocity of the ant with respect to the inertial frame, but it is written in the rotating frame. So I would say this is fine, but if you want to convert it to the inertial frame, because we have this angle, we can do that. So we can say that velocity in the inertial x direction is going to be the I component times cosine 30 in the I. Let's write it down. So V ant in xy direction, the inertial direction, inertial frame. So that is going to be, we can use a matrix notation to do this rotate, to do the rotation of the frame. This is basically, we have a frame that we want to rotate it, or we can just here, just project the vectors one by one along the x and y direction. So V ant in the xy, so that is going to be xy inertial frame. That is going to be Vx here, Vx times cosine 30 cosine 30 in the I direction, so capital I. And also the y components here, so I think I have to bring this down. The y component here also has the y component in the rotating frame has a component in the x direction in the inertial frame. So if I just draw a line here, this angle would be 60 degree. And the reason for that is that if I draw this line here, because this line is just perpendicular to the horizontal line, this line is perpendicular to this line, the angle between these two lines is going to be equal to angle between these two lines. So that's 30, and therefore this angle is 60 degree. So here the x component, the inertial x component of this velocity is going to be minus v y cosine 60, again in the I direction. So both of them are in the I direction. That's for the I. And for the j component, capital J component, we are going to have Vx sine 30, the capital J direction, plus Vy sine 60, the capital J direction here. And we can just, for Vx, we can just substitute 20, and for Vy, substitute half, minus 20 for Vx and half for Vy, and we get the velocity in the inertial frame. But as I said, this is also fine. So that's for question 2. Let's go to question number 3 here. So in question 3, we have particle P is sliding through the slot in link AB. This is actually, I think, question 4. Did we pass the question? Oh, so this was the third question that we solved, and this is the last question we had. So particle P is sliding through the slot in the link AB while it is attached to a string that is fixed at point A. So we have a ball, we have a particle here that is attached to a string, that the string is just pinned at point O. The bar starts rotating from horizontal position, so theta equal to 0. So the initial position of the bar is just theta equal to 0, with the constant angular velocity of omega 5 radian per second in the counterclockwise direction. That means in this direction. So this is omega. Basically, let me fix the pin here. This is omega direction, which is equal to 5. Find the velocity and acceleration of particle P as a function of time. And we are given that the length of the string is also L. So this is a problem this is a polar coordinate problem. So here, if we attach a polar coordinate to this bar, so here, or you can also just say that this is a particle again moving with respect to this rigid body and just take that approach. But this is just kind of like similar to the problems that we have solved for the polar coordinate system in the class. So if I just consider that this is ER actually, not X. So if I consider a polar coordinate that its origin is here, let me use another pen here, another color here. So also let's just make this a little thicker. So if I consider this is ER, it doesn't turn out to be good. Let me see if I can. I know that I was able to just draw a straight line here. Let me see if I can find it. So yeah, this is it, I think. So let me just delete this. just draw a straight line here. That's for the ER, and also this is going to be for E theta. Okay, so let me get my pen back here. Okay, don't need this. So this is ER, and this is E theta. So I have to find the position vector of this particle in the polar coordinate system, and once we have that, we should be able to, because we have theta also, we should be able to write down the velocity and acceleration of particle P here. So just to kind of like review, so the velocity of particle P is equal to, in the polar coordinate, is going to be r dot in the ER direction plus r theta dot E theta in the E theta direction. And what is r? So from here, the origin to this point is going to be r. So here, if I can just draw another straight line here. So here. So this is going to be r. So r. So we have to find this r based on this geometry that we have based on L and theta. And once we have r, we can just write down r dot ER, r theta dot E theta. We have the theta also, so because the theta dot is just 5 radian per second, so we have theta dot. So before writing down r, let's just write down theta dot. Theta dot is equal to 5, and also we can find theta because we are given the initial condition for theta. At t equal to 0, we are given that theta is equal to 0. So I can say that theta is equal to the integral of theta dot dt, which is going to be 5t plus c. So this is theta. And so this is c, the constant of integration. So at t equal to 0, theta is equal to 0. So we find that c equal to 0, because if I substitute t equal to 0, theta equal to 0, c turns out to be 0. So we have theta is equal to 5t. And now we have to find r. So we have theta as a function of time. We have to also find the r based on geometry that we have. So here, the triangle OAB is an isosceles triangle. So if I just draw this here, because this length is L, this length is L. So let me draw this triangle here. So this is basically B, this is A, and this is O. And I want to find this R. So here is the point, just kind of like the trick of this question is that, so the length of the string is L. So if this is equal to R, this is equal to L minus R. So L minus R, because this whole thing is L, so that part is L minus R. And because the length of the string itself is also L, so this part is going to be L minus R, and that's going to be R. So basically here, this R is equal to from point B to point P. So that's R. So in this triangle, I can say that this is L, this is L, this is theta, and this is R. And I want to find R. And just I figured out that also this side of the triangle of OAB is equal to R. So if I find this side R here, I have the R here, and I can just substitute it into my equations. So here it's just easy to just a little geometry. We can find R here. All I need to do is just to kind of like from point B connect to the midpoint of AO. And because these two sides are equal, that's gonna make an 90-degree angle with OA. So this is 90 degree, that is going to be R over 2, this is going to be R over 2. So now we have a kind of like a triangle with 90 degree angle. This side is R over 2, this side is L, and we should be able to write down, and this is going to be theta over 2, theta over 2. So this is going to be theta over 2, theta over 2. We can write down that sine theta over 2 is equal to this side over this side. So that is going to be R over 2 over L. So this is going to be R over 2L. So here we can just find out that R is equal to 2L sine theta over 2. So now we have R just based on L, the geometry, and also theta. And we have theta as a function of time. So I can write down R is equal to 2L sine theta is just 5t, so that's 5t over 2. And now all I need to do to calculate velocity is that to just take the derivative of R and also theta with respect to time to calculate the velocity. Same thing for the acceleration. I will write down the formula for acceleration. So let's just, with the velocity, let's continue here. Vp is equal to R dot. So here R dot is going to be very easy. So this is 5 over 2 times 2L, that's going to be 5L cosine 5t over 2 in the ER direction plus R theta dot. So we have R is just 2L sine 5t over 2, and theta dot is equal to 5. So this is going to be 10L sine 5t over 2. That's for velocity of in the E theta direction. So in the E theta direction. So this is velocity of point A, point P, the particle. For the acceleration, again we have the formula for the acceleration in the polar coordinate. So that's AP is equal to R double dot minus R theta dot squared in the ER direction plus R theta double dot plus 2 R dot theta dot in E theta direction. So again, because we have R and also theta as a function of time, all we need to do here is just to calculate some derivatives. So AP is equal to R double dot. So we have R here. R dot was 5L cosine 5t over 2. Again, if we take another derivative, that's going to be 25 over 2 minus 25 over 2 L sine 5t over 2 minus R theta dot square. So we have R theta dot is equal to 5. So theta dot square is 25 times R. So that's going to be minus 50 L sine 5t over 2. This is going to be in the ER direction plus. For E theta direction, we have R theta double dot. So theta double dot is equal to 0 because theta dot is equal to 5 constant. So that term is equal to 0. So plus 0 plus 2 R dot theta dot. So R dot, we had the R dot, the derivative of this term is going to be 5L cosine 5t over 2 and times theta dot, that's equal to, which is equal to 5. So that is going to be 25 L sine t over 2 in the E theta direction. Let me check to see if I got this right. So r dot theta, we have 2 r dot theta dot. So theta is 5 times 2, that's 10. R dot is 5 actually, so this is 50 actually. So this is equal to 50 L sine t over 2 in the e theta direction. And for VP, I think we got it right. So let's check again. So V is equal to, in the e theta direction, it's just r theta dot. Theta dot is equal to 5. R was 2L, so that's 10L sine 5t over 2 in e theta direction. Yeah. So I think we got everything right. So if I made a mistake in this calculation, or if you had a question, on each of these questions, and actually from now on, if you have any question for the lectures that we have online, as I said, you can just email me or just leave a comment on the video that I post, and I will try to answer your questions as soon as possible. Regarding the office hours on Wednesday, so I posted an announcement yesterday, that we are gonna just have our office hours at the same time, but just in an online format. So I'm gonna be available online on Wednesday, 8:30 to 10:30, and you can just, during that time, you can just send me an email to ask a question, whatever question you might have, and we can either discuss it through email, or if it is something that we need to just discuss it kind of like in a back and forth between us, we can just I can arrange a video call on either Skype or Zoom video call, and we can just discuss your questions. So yeah, that's it. That's for the midterm exam that we went through it, and I guess I see you in the next online lecture for next Monday. So before just posting this video online, I just checked the solution to make sure that I have done all the calculations right. And actually I figured out that we have done a mistake here in question 2 here. So here when we said that RCB is equal to minus 1.5 in the I direction, that's correct, that's RCB, but here we should write down RBC. So here, just let me correct this. Let me go to here. So this is going to be RBC, and therefore this sign is going to be positive, so 1.5 in the positive I direction. So here, if I just again correct this is going to be K cross I, which is J, so this is going to be plus 1.5 J, and if I go down here, so this is going to be 1 plus 1.5, again plus 1.5, plus 1.5, and therefore this is going to be minus 2 over 3 radian per second in the for omega BC. So that was one mistake that I wanted to fix. The other thing is that, so for this question we just calculated the velocity of ant, and I forgot to calculate the acceleration of ant. So let's here just calculate the acceleration of the ant here. So I think I tried to just write down this velocity in the inertial frame, and that's why I got distracted and didn't calculate the acceleration. So for the acceleration here, we have A ant is equal to point A. So again, we have a particle moving on a rigid body, and we are using that formula to calculate the formula for the problems that we had a particle moving on a rigid body. Here the rigid body is AB, point A. We are writing the velocity of the ant, the acceleration of the ant based on point A, which is pin. So it's a pinpoint, so the acceleration of point A, I want to have the figure and also have like be able to write here. Okay, so I think this is good. So that's point A, its acceleration is equal to 0 plus, so A ant is equal to AA plus alpha AB, alpha of the rigid body cross R ant with respect to point A plus omega cross R, and this is again ant with respect to A plus R double dot plus 2 omega cross R dot. So here we get acceleration of ant is equal to 0 plus alpha. So alpha here is just 1 in the positive k direction. So k cross the position vector of ant with respect to A, which is 10I here. So that's going to be 10I plus omega, which is minus 2k. So minus 2k cross minus 2k cross R, which is 10I, plus R double dot, that's the relative acceleration of the ant with respect to rigid body, which is here minus 5 in the I direction. So minus 5 in the I direction plus 2 omega cross R dot. So 2 times omega, which is minus 2k cross R dot, and R dot is just half a meter per second in the I direction, so that is going to be 0.5 the I direction. So this is going to be equal, acceleration of the ant is equal to, so this is 0, here we have k cross I, that is j, so we have 10j, and here we have k cross I is j, k cross j is minus I, so that is going to be 40 minus 40 in the I direction, because we had 1 minus and we have k cross j, that is minus I, so we have minus 40 in the I direction. And here we have minus 5I, and the last term here is, so 2 times 2, 4 times half, that's 2, and here we have k cross I, which is j, we have a minus sign here, so that is minus 2j. So we have 10 minus, we have minus 14 minus 5, that's minus 45 in the I direction, plus 8 in the j direction. So again, this is the acceleration of the ant with respect to the inertial frame, but it is written in the rotated frame. So if you want to convert it, to write the acceleration in the inertial frame, we can just use this formula that we had for the velocity, but here we would just substitute ax and also ay and use this formula to write the acceleration in the inertial frame. But as I said, this is also fine. You know, all we have asked for is just the acceleration, velocity and acceleration in the inertial, with respect to inertial frame. So I think that's all for this question. That's all we asked for, velocity and acceleration, which we calculated both of them.